All right, good afternoon. Today we are going to talk about mechanics of material lab, the theory and how you should write the report and everything. Hopefully we're going to cover all the material. It's going to take a while to cover all the material here. So let's start by talking about measurement. So let me share whiteboard. All right. So in general, in this lab and every other lab, we're more concerned in measuring things rather than just writing equations. So basically, the purpose is to use the measurement to validate, either reject or validate the theory. That's the general idea of going to a lab. So now the first thing that comes to the mind is how do you measure? So let's write it here. How do you measure? And this looks a little bit funny because the answer to this may be extremely simple. They say, well, just find a caliper or a ruler and just measure it, right? But in fact, it's not that easy. So let me give you an example. Let's say you have a cylinder, a bar, and this is to you in the lab. And I give it to you and I say, I also give you a caliper. So this is your caliper. Let's draw it here. Is a digital caliper. And then I say, measure it, measure the diameter. What is D? The diameter. And well, what do in this? So I would like to somebody just step in and give me an opinion. If I ask you find the diameter using a caliper, what do you do? And how do you report it to me? Any idea?
To find the diameter of that pipe?
Yeah, like diameter. Put it here,
would,
the outer diameter.
Yeah, I would use the calipers and go around the pipe and give me a measurement like 1 inch. 1 inch diameter.
Okay, so you just do one measurement, right? Is that what you do?
Yes.
Okay, well, that is a perfect answer when you have a theoretical specimen that the diameter is the same, right? But in the real world, we have something we call a manufacturing error, right? So the diameter, in fact, is not everywhere the same. So if I just follow your step and say, well, I just take this caliper and I just put it, for example, here, and I just simply measure the diameter here, and then I report diameter is, for example, 1.2 inches. Well, this is, we call it a rough approximation. It's not accurate, it's not a scientific measurement. This is not what I actually expect in this lab. So in fact, this bar, as you can see, this bar has some tolerances, some manufacturing error. So sometimes, in fact, if you have this bar under microscope, you have variation in the diameter like that.
Would it not be better to take 4 or 5 measurements and then average them?
Yeah, go ahead.
Would it not be better if you took 4 or 5 measurements of the same bar and then took an average to
Exactly.
get the diameter?
Exactly. That's exactly what we are going to explain right now. So I was actually right now, I was trying to reach to this conclusion that we need to do multiple measurement all the time and then take the average. Okay. So let's consider exaggerated picture of this pipe in the real world. As you can see, you have some sort of deviation in the diameter. Somewhere is thicker, somewhere is thinner. So what I would do, I would grab this, when I take the first measurement, let's call this D1, is 1.2, and let's say put another one here, 1.21 inches, right? Then I take this caliper and I measure somewhere, like, right? And then I read it. And then this is going to be my D2. Now I read 1.20, for example, of inches, right? Then I do another one, D3. Then I simply put my caliper right here. There you go. And then you read D3, 1.19 of inches. And so 3 measurement is fine in this lab, although it's recommended 5, because you see, according to the rules of statistics and probability, we have something called central limit theorem. So the more measurement you have, the better pool of data you have, the more accurate you mean or expectancies, right? This is, we had it before. So, but here, this course, only 3 measurements is enough. In fact, the data give you, sometimes the average is also taken already. So you don't really need to do that, but sometimes it's not. So you have to take the average. So let me put my caliper here somewhere else and there. So get 2 more data. So let's say D4, 1 point, again, I get 20. Sometimes you get repeated data, which is fine, absolutely no problem. And then you get D4, 1.23 inches. Now this is your generated data. You can just continue going on and generate a lot of data. But if your boss or your advisor or whoever he's asking you to do this experiment is asking you to report the diameter, you just simply don't say, well, you know, my diameter is D1, blah, blah, D2, blah, blah, D3. This is just not going to work. You have to report one number. So, well, the easiest thing to do that here, to just report one single number, is to say my diameter actually is summation of diameter divided by number of samples, or simply is the average. Usually they put bar on it, meaning average. In this case, let me put this in the calculator. Forgot to bring my calculator here. Okay. So I put this in my calculator. The average is 1.21 plus 1.2. Divided by 5. So the average after round up to 3 significant digits is 1.21. Okay. Now, is that enough? That means if I just report and say my average is 1.21, so my diameter is 1 inch and 21 over 100 of inch, and that's my average. Do you think that's enough, What is your suggestion? What else can you provide your team such to have more information about this pipe or set of measurement in this pipe? Any idea?
Maybe a tolerance.
Exactly.
Yes.
Exactly. The answer is the tolerance. Or sometimes you have different vocabulary. Some people call it tolerance. Some people call it error, and by mistake, some people call it uncertainty, which is a topic. Sometimes it's used here that how much of certain are you about this measurement? It's kind of like it's related, but not exactly the same thing. So that means if I want to report how accurate this measurement is, I need to have another parameter that we show it with delta or error in D. So how can I find that? Well, the first thing you may say is a standard deviation. Okay, that's absolutely right. It's used in a lot of labs and it's very standard. So what they do, they find the standard deviation of the set of data. But the way we do it in this lab is even easier than that. We just say, well, if you graphically represent this data on an axis like this, so this is your tries. Let me bring this down a little bit. And that's your D, okay? And this is your average, which we already have. The average is 1.21. Okay, so if I plot my data, so let's say this is try number 1. I need more color. Try number 1, 2, 3, 4, 5. I plot this data on this set of weird looking axes. Then for D1, the measurement of D1 is 1.21, right? It's right on the average. So this is my D1. You see that? Now, if I want to plot D2, then I go to the next try, and it's a little bit less than that. This is my D2 because it's 1.20. We can put another X label. So this is 1.20, 21, 22, 23, and this is 1.19 right here. You see that? So now for the third measurement is 1.19. It's right here. And then for the fourth measurement is again 1.20. And the fifth measurement is 1.23, sorry, which is right here. You see that? So the data are not exactly on the average. They're kind of like, we call it clustered about the average line. And what does this clustering mean? That means that if you continue getting more data and more data and more data, you get a pattern like that. You get another point here. Of course, I should put it at the top here. You get another point here. You get another point here. You get another point here, 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 here. You see, all your data is going to be in an envelope. So let's show this envelope by blue lines. This is your maximum possible of your envelope, and this is your minimum possible of this envelope, right? So all the data, regardless of where you what pipe you measure, all of it would fit in this envelope, which we call it clustered or collected about this center line, right? So if I want to say here graphically, if I want to find my error, what should I do? I mean, well, there are different approaches, but the way we can systematically introduce an error is to find this radius. You see that? If you consider your envelope to be like a envelope, like a cylindrical envelope that gather all your data, you see that? That's gonna be from here to here is going to be of like radius of this cylinder, the envelope that collects all your data in, all your measurement. So we are interested to find this radius, and what is this radius? We call it delta D, because this is D, and that's the error in the D. This radius, in fact, is error, right? Delta D. So if this is my max, let's denote here D max, and the minimum one is D min. Now I want to ask you guys, give me a formula. So let's write it here. What should I find for delta D? What is the formula for delta D in the term of D max and D min? D min and D max. So if somebody gives me D max and D min, what would be the formula for delta D? Any idea? You can look from the picture, you can find the formula immediately.
The max minus the min.
The max minus the mean is going from here to here, the length of this vector.
Max minus min divided by 2?
Exactly. That's exactly right. So here, delta D, let me write it here. This is the first formula that we used. Delta D, or error in D, is equal to D max minus D min divided by 2. And according to this picture here, it's so obvious. Well, if you have this upper bound, there you go, D max, and you subtract this upper bound by lower bound, D min, then you get the length of this vector. And in order to get a half of it, which is delta D, you have to divide by 2, right? What about D average? What's the other formula if somebody gives me max and min, just two numbers, max, min, not all data? How can I estimate average, estimated? How can I find the average just by using D max and D min? Now you should be able to give me this formula. Any idea?
D max plus D min divided by 2?
Exactly. Thank you so much. D max plus D min divided by 2. That is a formula that if you have just two numbers, the upper bound and lower bound, 2 maximum minimum, you just simply add divided by 2, which gives you the center of that cylinder, the envelope, right? So these are the formula that you need to use when you do measurement. So now let's go back to our pipe measurement and using caliper. Now, what would be my error or delta D? The first person finds it as a bonus. So delta D, use your calculator. Delta D is equal to
0.02.
0.02. Let's see if we get 0.02. So what you do, you just use this formula here, highlighted with green. You get max Max here is 0.20 minus mean, which is 1.19 divided by 2, which is 0. So if you want to report to your boss, you report 2 numbers. So let's write it here. You report the average is equal to 1.21 inches, and then delta D is equal to 0.02 of inch. That's kind of like uncertainty or error in your measurement. Now, Sam, please email me after this class if I forget to put your bonus on file, because we're going to have a bonus grade for this class that's going to cover, in the case of like not good reports or misreports, or, I mean, you can get several bonus, 2, 3, 12. And then they're going to, according to the weight that I'm going to assign them, they're going to cover some reports, maybe 1 or 2, or maybe 1 just, or missed classes or whatever. So try to contribute. I mean, do your best to contribute to the class. All right, so this is what we have here. Now, I want to ask you something. Let's say let's take another page. Let's say now I have a pipe is manufactured and is a very high quality pipe. So the diameter is pretty much the same. They use a CNC machine to create this pipe. So if I can draw a straight line, and then you take your caliper, you put it here, and you report what you read is 1.D1, .19, D2, then you put it here, and this is again 1.19, D3, 1.19, D4, 1.20. Now you can immediately say that because you use a CNC machine to manufacture this pipe, even before measurement, you could tell measurement is going to be very accurate, right? Now, after you do this measurement, you can immediately say that your measurement is accurate. Why? Well, let's draw it graphically. Exactly the same thing we did before. So let's put 1.19, 1.20, 1.21, 1.22, 1.18, 1.7. So if you do your steps 1, 2, D3, 4, 5, whatever, then you get D1 here, D2, D3, D4, which is your here. Now look at your envelope. The envelope is kind of like this. You see? So you get narrower. So the diameter of this envelope contains measurement thinner and thinner. Which means, so what was half of this? Half of this diameter was delta D. So what was delta D? The error goes down. So now you see the graphical correlation between the actual real world and your measurement data, the set of data. Okay, so let me summarize this section of measurement, that every time you do any measurement of any quantity, like diameter, length, modulo of elasticity. Of course, modulo of elasticity comes from tables. So you have to get multiple values from different tables and again do the same thing. Max plus min divided by 2 is the average. Max minus min divided by 2 is the error, right? But the thing that you can use with the caliper, diameter, length, and like mass, you can use a scale. You have a lab, measure several times, find the average, find the error, right? And so on, etc. All the physical quantity. You have to report 2 numbers. So far, we before this course, we always thought, well, we only need to report the average. But in this course, we're going to add also the error. The average is designated with the bar on top. The error is designated with delta. So this of this, right? The measurement. Now let's go to the next section. When you do, let's add another slide. When you do measurement of things in this lab, we are trying to validate something called a spring constant. So let's talk about the spring constant. So everything we do in this lab, everything we do in this lab, in different experiments is to either validate or reject the theoretical formula for something we call a spring constant. And what is that? Now, I want to talk about the spring constant. Well, according to the basic physics, we know that, well, if you have a spring and you fix one end, maybe to wall or some other mechanical system, and then you apply a force to the other end, this is going to deform. So you're going to get some sort of deformation, like, and then you have a deflection, delta. And what happens here with the same amount of force, you get deflection. And the formula for that was F is equal to K delta. Okay, sometimes they put a negative sign here. We're talking about right now the magnitude. They put a sign to show that it's in the opposite direction, that the spring applies to the system. But here, we just talk about the magnitude. So if I actually give you an actual spring, which is a subject of first lab, right, the first experiment. First experiment, I actually give you actual spring, the physical spring. So it's a spring, it's a coil like that. It has 2 ends. And then you apply different forces to it, you measure deflection, and then you find the spring constant. And you compare it with the theoretical formula. But what happens here in the next lab, beam deflection, torsion, things like that, you will never see an actual physical spring. And then when I say find the spring constant, you get confused. For example, this specimen, this is MLA. So this is your specimen. And you put this standard specimen, you put it in the tension machine. So you fix this end to one end of the machine. You got hooks here. And then you have another end to go. you fix it to the other end, okay? And then the machine is going to apply tension force to this end, F, and then after some point, you see this specimen will break, right? Now I say, find the spring constant. And then we had a student in the lab, they were trying to find the spring, just looking on the table, where is that the spring? Well, what I want to now, this specimen spring, but how come? How come this is a spring? Well, when you apply this force, what happens, this is going to go, because it's called elastic material. In this lab, elastic material. Sometimes they call this lab elasticity, because we're talking about material that they can change the length. So that means when I apply force here, this specimen is going to form. So I'm trying to draw the deformed form. So it's going to shrink a little bit, and the length is going to increase like that, you see? And these holes are going to shrink a little bit like that, and get thinner like that. You see that? When you apply, when these two jogs, they go actually in the tension mode, they keep some distance, then this specimen started to shrink like that. And as you can see, we get some deflection. Do you see that? That's the deflection from here to here, delta. So I know that there is a relation between this force and this deflection. And if I plot it, it's going to be like that. Deflection, force. It's going to go up like that. And then it flattens, goes a very long distance, and then it breaks. And after here, you don't have more point because the specimen breaks, okay? So consider this region right here. We call it linear elastic region. Because you see, you can estimate this region with just a single line. Do you see that? So what is the slope of that line? The spring constant, K. Compare it with this equation. You see that? So even though I don't have actually physical coil like for a spring, but this specimen behaves like a spring. And we have a spring for that. Any question? This is very important, this observation. Any question regarding this? All right. Now let's go to another example. Let's go to, add one more slide. Let's go to a beam. So a beam, I probably it's better to use a color. So beam is one of most frequent components in engineering design. Okay, like that. So the cross section, this is a C beam. You see the cross section is like C. And let's fix it here. Let's weld this to the wall. So we're doing some work around it to the wall. And this is wall. Wall. Okay. So this kind of three-dimensional beam fixed to the wall. One of the lab experiments we do is exactly this. And we kind of load it with some force. Let's put the F here, for example. And then you read the lab manual, and then you see the lab manual is talking about a spring constant. And it gives you a formula. And it gives you a formula. And then it say evaluate the spring constant. And then you get confused. How come this is a spring? Well, you go back to the previous slide. You say any linear elastic material that can deform under the given force can be considered as a spring. Here's a basic definition. So you know that if this force F is applied, the first time F is 0, right? When you increase this F, let's say you increase it to is equal to 1 kilonewton, right? Then what happens for this material? This material is going to nose down like that. You see it going down a little bit. And then you have some sort of cubic line for deflection. You see that? And if I, let's say, if release the force is right 1K to bring this here, F is equal to 1K kilonewton. Now I ask you a question, if I release this force 1K, what happens? If I just say, well, let's just remove that 1K.
It would return back to its original position.
Exactly. That is exactly the same analogy with like a simple spring. Let's say here we have a spring instead of this part. Let's say I replace that system with the analogy of a spring mass, and then you put F here. Okay, when F is 0, you don't have deformation. Then when you have 1K, this is going to go like get compressed. Do you see that? F is equal to 1K. And then you have some sort of deflection, delta. So what I want to say, when you see a spring constant, because you see it in every single lab, we're talking about spring constant. The spring constant. Don't get confused. Do not get confused. Because every single linear elastic material in the world behaves like a spring. And now, when the report is asking you find the spring constant, you don't need to be a mathematician, or you don't need to have a previous background in mechanics of material course, the theory of elasticity. All you do, you go to the lab manual, and all the formula is given to you. If the formula is not given to you, then let's write it here. This is very important. If the direct formula for a spring constant is not given to you, sometimes it's given. If it's not given to you, another formula is important part that relates the force and the displacement is given. And all you need to do, so let's highlight this part, another formula that relates the force and the displacement is given. So again, you don't need to have a previous knowledge of mechanics of material or elasticity. This formula is given to you. All you need to do is to write in a standard form, in the standard form, F is equal to K delta. And this K becomes something that depends on the parameter of this formula. So all you do, you just rearrange this formula such that on the left side, you see here on the left side, you have force, and the right side, you have something times displacement. That something is your spring constant. All right, example. Another slide. Let's go back to this bar and let's fix this end to the wall. Put some welding here. And let's apply force F here. And then one of them, before you actually start writing your report, is to find the formula for the spring constant. Well, you go to the lab manual and you see the lab manual is talking about Hooke's law. Again, you don't need to have knowledge. This Hooke's law is given to you. The lab manual gives you Hooke's law, which is equal to sigma. S is equal to Young module of elasticity times the strain. Again, you don't need to know this equation because the lab formula also tells you sigma, the stress, is the force divided by cross-section area. So consider a cross-section area here. So consider a section cut of this. Consider this area is A. So the force divided by area is sigma, and another relation in the lab manual, the strain is delta divided by initial length. So the strain or relative deformation is the change in the length due to the existence of force F divided by initial length, right? So let's say this is the initial length, undeformed length, L, and after you apply this force, your strain going to twinkle a little bit and deform. Again, some exaggeration like that, you see that? And this is your actual deformation, delta, in meters. Now, this relative delta over L is called the epsilon or a strain. Now, the question right now, find the formula. Right now, you have everything you need to find constant. Find the formula for the spring constant. Now start working on it. The first person who find this formula will get 1 bonus. So use this information. Go back to the previous slide. The previous slide, it says you have to, all you need to do, look at this paragraph, all you need to do is to rewrite the formula in the form of force on the left is equal to something times delta. That something is a spring constant. So this is all your information. How do you find the spring constant? 60 seconds.
Is it the theta A equals K delta?
Not quite right yet. This spring constant formula, it should be in the term of the length and other physical parameters of this bar. So it's kind of like a nice formula, a good looking formula. Let's make two worth of 2 bonuses. Because this is a little bit, the first time you do that is maybe a little bit hard. The first time you do is usually hard, but when we understand it, it becomes easy. Okay, I'll go ahead and solve it myself. Do you need more? Let me solve myself. So, Brook is getting close, but it just needs one extra step.
Would it be
Yeah, go ahead.
F equals AE delta over L?
You see, the spring constant should be independent of deflection. The formula for a spring constant, it should be independent of both force and deflection. Look at here, when you have F is equal to K delta, right? This by itself should be independent of force and independent of delta, because later on this will relate both force and delta together. So this by itself is independent of force and delta. So you should not see F and delta in your formula. Now let me go ahead. We're going to have more opportunities. Let me go ahead and solve it. So look at this equation. Let's substitute sigma here, right? F over A here in the sigma, and let's substitute epsilon here. What do I get? Sigma is equal to F over A is equal to E times, instead of epsilon, I put delta over A. Right? So according to the previous slide, it says all you need to do is to write it in the form of force on the left is something times delta on the right. So let's do that. Keep force on the left and then just multiply both sides by A. Let's see what we get. If you multiply both sides by A, then we get F is equal to keep the force on the left. You see that? AE, and bring the L out times delta. That's exactly the same equation that I had before. So what is my spring constant right now?
AE over L.
Exact. AE, that's your K. So a spring constant is AE over L. You see that? It's independent of delta and F. It depends on the cross section. It depends on the Young module of elasticity, and it depends on the undeformed length of the specimen. Now, another example. Let's add another example here. Let's say you have a beam here. On these two support, and you apply a force here, and obviously this beam is going to deflect like that, you see, and then you get some delta here. And from the mechanics of material course, you have a relation F is equal, for example, 132 EI module of elasticity times delta L square. Let's put it L cube, and this is L. A relation, something like that. And this given in your lab manual, for example. Now, if I just ask you find the spring constant, right? What do you write? What is the spring constant here?
L cubed over 32 E.
Exactly. L cubed 32 EI. You see, it's independent of force and deflection. Now, when you find the spring constant, then you're like half 50% through the problem. Like a major part is to find spring constant formula. It takes, because sometimes the equation is not straight like that. You have to substitute some equations together to get that formula. But after you find the spring constant, then your work in actual substitution begins. So let's go to a typical report for report number 1. This is actually the first report you need to write. So let me walk you through that. Here, share content screen, Zoom. Start broadcast, okay. All right. So, do you see my screen?
Yes.
Yes.
Okay, okay. Well, I'm glad that I found this option here on iOS. So basically, this is a typical lab manual. The first part is basically introduction to the theory and why you do that lab and things like that. So you actually kind of skim through it. And then you see here in the first lab, the formula for a spring constant is just given right away. You don't need to do any manipulation, substitution of equation. It's just right there. K is equal to G D to force power over A, D to the third power NA, and all those parameters are explained here in the formula, in this figure. And then you go ahead and read, and it's talking about objective or lab approach. All you need to do and do this. Well, this part of data acquisition and preparation, obviously you don't do that. Why? Because of course we don't have access to the machines, so we any kind of, so instead of filling out these tables, so you just go to the Excel file and you see the tables are already filled. So what previous students, the measurements are done and the table are filled, and all you do, you just quickly read through this, make sure you understood different parts, how they're obtained by measurement. And now this is basically, this is going to talk to you about example of like calculation. You don't really, I'm going to talk about this calculation, so you don't need to read that. Now the actual work starts from here. You see that table, table number 1, the first table in the lab report, that is probably the most important part of your lab report. So the first, in order to grade your report, the first thing I do, I read this table and try to duplicate some of your result, whatever you report in this table. And your grade, you know, of course, you know, things like should have caption underneath, and you have to have page numbers. You have to also have your name in it. Of course, you have to follow the formatting instruction and answer these questions, of course. But most of your grade is based on this table. And now I want to talk about this table that, in fact, when you get your spring constant, let's connect this topic to the previous topic I was talking, the spring constant. When you get the spring constant, this stop table all talk about the spring constant. So K is in fact your spring constant. And you see here, you have K sub pred. You see that? That's K predicted. That means K theory. That means the K that comes from that little formula right here in the first page. Or the K that you obtain. This K is given right here, right? If it's not given in the next report, then you have to find it by substituting the exact you did. So when you get K here, then you need to put here the capital D, the lowercase d, NA, and for example here, capital D is the center to center diameter of the coil, and lowercase d is the thickness of the coil. What do you put here instead of capital D and lowercase d? Now I ask you this question. Do you put your, as you know that, like if you want to put, if you want to measure your thickness, you do marker measurement with caliper, right? You measure the thickness of some part of it, and then you go to another part, and then you have like 4 or 5 data for lowercase d. So what do you need to put in this formula? Do you put all 4 of them in this formula?
You put the average.
Exactly, exactly. That is the point. You put the average. So after you kind of compile all your different data into one average, now you're talking about one quantity. Now this formula, you put the average here, the average for lowercase, the average for capital D, and also G is shear module of elasticity, is a number. You don't measure it, you get it from tables. There is a website you see here, mathweb.com. You go there, you put your material property there, and you get G. But sometimes that G has a range. So mathweb.com gives you a range. It says G is like, for example, 200 gigapascal plus minus like 10 gigapascal, right? So it's gonna give you the average and deltas for that G. If it doesn't give you the average or delta, then you go to another website on Google, right? Then you go to another. There are always several resources for the same quantity. There are several different tables. So you get different values. Then how do you get your average? Well, you just do sum divided by number of different sources that you find. How do you find your delta? You say max minus mean divided by 2. So basically in this equation, you can put all the averages, right? And then if you go back to this table, let's see, how can I go back? All right, I think I should scroll from here. Okay, we go back to that table. So here the formula say K predicted, which is that formula when you put your average in it. And then when you get your answer, you just put your answer here. Some teachers say, well, you have to keep 3 significant digits, otherwise I'm gonna deduct some grades, and I'm not gonna do that. So don't worry about it. If you put like 3 significant digits or 4 or 5, those are not important for me. For me, the important part is how you find that K equation for K predicted and how you do sensitivity analysis. We haven't talked about sensitivity analysis yet. I'm going to start talking about that, which is, you see here, it says delta K over K. That is coming from sensitivity analysis. Now let's talk about sensitivity analysis. All right. Now, after we talk about that, then we have 2 more columns, K observed, delta K over K observed, and then you're ready to rush and submit it to me. Okay, so you can start basically from today, and if you have any question, you can email it to me. Don't forget that you need to write 2 reports per week. So it probably takes all your time. And I know that you have mechanics of material, and that course is extremely dense, which I never recommended for a student to take that in summer, because summer terms are short, and you know, that is the semester sometimes. So anyway, if you work all the time, you will be able to succeed. But if you just say, well, let me take a break, you know, I can do it tomorrow or maybe next week, unfortunately you will face with problems. So Now let's go back to our discussion of stop broadcast here. Okay. Let's go back to the discussion of that thing lost all the previous slides. That's weird. Let's go back to the discussion of delta K over K, or sensitivity analysis. So here I put title sensitivity analysis, or some people call it error analysis, but in fact, this part is sensitivity analysis, mathematics. And this is a very mathematical thing, but it gives you wonderful insight into your measurement, how accurate your measurement is. Now, if I know that, well, going back to the example of pipe, if I get a pipe like that and my boss asked me to measure the diameter according to the discussion we had, I report him an average D and a delta error in the measurement D. And you know how to do that, right? It's on this before. Now, the question here is, well, I want to investigate this relation for K. K is equal to, we found it before, AE over L, right? Do you remember that? Now, my boss asked me, how accurate is this estimation for a spring constant? Well, I can answer him already how accurate my measurement is for D. But how can I answer him how accurate my measurement is K, spring constant, right? In fact, how can I find my delta K? Like the way I did with delta D. How can I find my delta K? Any idea? The question here, if I have this pipe and somehow I generate different data for diameter, let's put in this table, diameter and E and length, and because I have diameter, therefore the last column I have A, right? The A is simply pi over 4E, right? So I have A. So let's say for this, I have the average, and then delta for every single individual. How do I get this? From the measurement. We already discussed it. Now, how can I use this information to find delta K? Any idea? Let's do 2 bonus for that. 2 bonus. It's in fact a little bit hard. This question is hard. You remember we talked about the envelope, that if this is my average D and my data are kind of like clustered about this line like that, if I measure how many data, they get clustered about that line, and this is my max, E max, and D min. So my average D is max plus min divided by 2, which is just average based on 2 numbers, max min, approximation, right? And the delta D is equal to max minus min divided by 2, is minus, right? So can I apply the same to find delta K, because you see, we were talking about this is like a dummy variable. It can be D, can be K, it can be E, can be L, right? So let's apply this concept to that. So what would be my delta K? Give me the formula. Well, I use this formula. Delta K is going to be K max, right? Minus divided by 2. The problem is solved. But you say, well, hold on, wait a minute. What is that K max? And that's a very good question. Now, what is K max? What, based on this different data that I get for D, E, L, you see that here? This has 3 parameters. At what point the maximum K happens? Can you answer the question?
Would it be your largest values for A and E and your smallest value for L?
Exactly. Thank you, Sam. So this is the key. Well, you have a fraction here. You remember we have a fraction A over B. This become maximum when the denominator become minimum and the top become maximum, right? So if I go this for K, I can write just immediately K max is equal to when A is maximum. When do I get A maximum? When A become the upper bound. Look at this upper bound here. Upper bound of your measurement. So what is upper bound of my A measurement? Is A plus delta A. A average. You see the middle center line is average. The average plus is my bound. See that? Times. What is my maximum E? E average plus upper bound. Now what should I put for the bottom? The minimum. When do I get the minimum for L? When L become L average minus delta L. Interesting. You see, all this average is deltas here, delta A, average A, already. These are a bunch of numbers you put in this table. You have average L, delta L already, you have average E, delta E, and then you already have average D, delta D. Do you see that? So you have average of all these numbers. These are a bunch of decimal numbers. So you all you need to do is substitute here. Then you get your K max. So what is the formula for K mean? Because if I want to find, you see, my objective is to find delta K. Why? Because I want to put it in that table. That table is asking for delta K. I want to fill out that table and just finish my report, right? So you need to find delta K, and for delta K, we already found delta K max. And how do I find K mean?
Would it be
The
your
smallest numerator and largest denominator.
Yes. So K mean, can you tell me the formula?
A average plus or minus delta A.
Okay.
Times E average minus delta E
Perfect.
divided by L average plus delta L.
Perfect. Thank you. Email for bonus. Thank you. That's your K mean. Right? So you have K max. This is going to be, look, this looks a little bit like scary. It's weird. But when you put numbers in it, you get, like, for example, 2.0 13. It's going to be, this is going to all boil down to a number, right? So the formula is a little bit scary, but when you put the number in it, it's going to boil down to a number, right? And also, going to, for example, 1.18, just consider some example, k-mean. And now what would be my delta k? What would be my delta k? Simply subtract max 2.13 minus 1.18 divided by 2, which is again a number, right?
0.475.
Right, which is a 0.475 and a number, okay? And now, if you go back to that table, then you see you have to find delta k over k. And what is that k? Is the k average that you already have. You see, the k average is from this formula. So you put the averages here from this table, you find your k average, you divide it by that. So you divide this number by this number, you put it here, and then you have delta k over k. So this is delta k over k theory. So let me create that table. That table you have k average predicted. Sometimes you see k average theory. Both are exactly the same. That is talking about AE over L, the average, k average. Then you see delta k over k predicted or theory. What is that? That is the formula that we derived. Okay? So the formula that we derived, you calculate that number and put it here. Again, this is theory. This comes from the theory. And then we have two more columns, delta k, like the k predicted here, k average, but observed. I'm going to talk about this. So you have OBS, that means observed. That comes from the measurement, that comes from machine, the observation, right? And then you have delta k over k average observed. Look, these are different. This comes from the formula that you put in. This comes from another thing that I'm going to explain. And then you have relative error. And then you have max error. Again, I'm going to talk about it. Today's session is just long because you have things to discuss. Now, when you fill out this table, then you are pretty much done. All you need to do is to answer the questions. Don't forget that. You have to answer the questions. If the question, your approach doesn't fit, because sometimes you say NA. For example, you have validated the result. If you validate, then what was the source of error? When you just simply say NA, because you have already validated, right? And then you're pretty much done. Don't forget, when you do derivation, again, do not waste your time. Do not waste your time typesetting. Beautiful mathematical formula. Just use mathematical formula. Just use a pen and pencil, just like a scratch paper. I mean, don't worry, it's not going to be like disrespectful or offensive. Just like treat it like a scratch paper. But try to do a lot. Try to drive a lot of equation. Try to do a lot of calculations, because I want you to learn, right? I don't want to see a beautiful document. Once you do that, just take a photo and put it in the appendix. put your derivation in the appendix. So I want to see, for example, here you put a number, for example, 3.11. I want to see how you got that 3.11. So I go to the appendix here, and I see, well, you're just driving some equation, or you do some fitting to the curve, and the slope of the field line and things like that. So I want to see that. I want to see every numbers here, like 1%, 1.2%. For example, I want to see how you got that 1.2%. So that's the reason that I say, print, please include all your scratch paper. Whatever you have done in this lab, just take a photo and include it in the report, so I can see your thought process. Okay? All right. So now let's go back to computation of delta K over K. This method that I taught you is called high-low. Let's put it here. This method is method A, the first method number A. High-low, like buy-low, but this one is high-low method. Why do we call it high-low? Because we find, you see that max, look at here, we find K max, we find K min, high and low. And then we use this thing to find delta K. You see that? So that's the reason we call this method high-low, because it's based on the high and low, right? But look, sometimes this equation for a spring here is just extremely easy. Here the equation is K is equal to AE over A. We can estimate, well, the high is, for instance, is A plus delta A times E plus delta E divided by L minus delta L. And the low is the opposite, because it's a simple fraction, and you can find high-low, right? But look, sometimes high-low is not possible. The equation is a little bit complicated. For example, beam deflection. You have a third order polynomial combined with the fraction. So in fact, you don't know where the high happens, right? It's like, do you remember from basic calculus, they said, find the maximum of this equation. And then you say, well, I don't know, I have to plot it, because it can have several maximum minimums, right? Then you use derivatives to find the external point, to find the maximum minimum, things like that. Now, in order to cover this limitation of high-low method, I want to introduce a method B. So let's go to another slide. Method B. To find delta K. This is called the partial derivative method. Partial derivative methods. Now, this is the preferred, let's put the green check mark here. This is the preferred method, is highly robust. It can be applied to all problems, regardless. And you don't need to know the high and low. So it's applicable to everything. And that's the reason I put a green check mark here, because I prefer this one to high-low. When you write your report, if equation is simple, like a simple fraction, just do high-low. But if the equation is complicated, for example, in one of the reports, we have beam under torsion. So you have a torque that causes this thing to twist. So you have some sort of like twist, and this is like, you go like twisting here, right? So, and then you have twist angle and things like that. In that case, the equation is very, very complicated. You cannot use high-low method to find delta K. So I want to see your partial derivative method for delta K. So where you apply the partial derivative method to all the problems in this course. And it's not really that hard. Once you know how to do partial derivatives, it's probably easier than high-low. So let's go back to a review of differential calculus. So in the calculus, we have, if we have a function of several variables, start with a simple variable, x. If we had y is a function of only one variable, then delta y, or the differential in y, is df with respect to x times delta x. Right? Do you remember that? Basic differential analysis. You guys did not see this in the calculus. So I assume that you have this, the basic differential, one variable differential. Now, if you had a function, let's say y was a function of two variables. Let's say instead of y, let's just call it omega. Omega was a function of xy, f of xy. Then what is the expression for delta omega? What should I write? Bonus? "60 seconds, this is just basic multivariable calculus. What should I write for delta omega? Omega is a function of two variables. Well, if you need to review, it probably won't take more than 2 hours to go to your calculus book and go to that page of like differential, and then you will find out that delta w in this case is going to be partial derivative f with to x delta x plus partial derivative of f with respect to y delta y. That is the formula. Now let's say I have a function, w now is a function of three variables, x, y, z. Now what should I write for delta w? Just look at the previous formulas and consistently, you need to constantly extend those formula for three variables. So what should I write here? Well, it's going to be partial f, partial the first variable, whatever it is, delta x, plus partial f, and second variable, whatever it is, delta y, plus partial f, partial z, the third variable, delta z, and so on. It doesn't matter how many variables you have, right? You can generalize this to many, many variables. Now, I will use this technology because this is like a mathematical things that as an engineer, I'm not really interested to do this kind of math. I want to use it for my engineering purpose to find my error, right? So what was my interesting part? Delta K, error in K, which was a spring constant. So how can I use this technology to find error in a spring constant? Well, let's say f here, you see, we consider the dummy variable f. Let's say this f, let it be your k, the spring constant. And then you can use exactly the same formula to find your delta k. Going back to our example, k was, one example, k was AE over L, right? So delta k, what should I write for delta k using partial derivative method? Well, you first notice k is a function of three variables. What are those three variables? A, E, and L. Do you see that? K is a function of, in this particular example, three variables, A, E, L. So what is my delta K? Consistently use this formula. You say the derivative with respect to the first variable, which is partial K, partial A, delta A, plus the derivative with respect to the second variable, partial K, partial E, delta E, plus the derivative with respect to third variable, partial K, partial L, delta L. That's it. And I didn't do new except to use copy paste from the calculus 2, right? Nothing new here. Now, am I done? Obviously, as an engineer, I'm only interested in numbers. I'm not interested in the formula. So how can I get a number out of this expression here? How can I get a number? Well, you look at here, you say, well, I have this from table. This stuff I already have a table of measurement. Table of measurement, because I already did my measurements and I computed them, right? I found the average, I found all deltas and everything, right? So if I had this stuff, the derivatives, then I could simply plug it in and do the algebra on calculator and just get the number, right? So now we're talking about computing derivative. I ask you this question, what is the value of this derivative? Anyone can compute it? Delta K over delta A. Let's go step by step. First we find that, and then we work on the second derivative, and then we work on the third derivative. So what is delta K over A? Partial K, partial A. The derivative of K with respect to A. What should I put here? And don't forget, your K relation is right here. So you have to take the derivative of K with respect to A. So what do I get? Let's go to the chat room. Hussein is not here. Samuel, Ruth, Benjamin, Michelle. Okay. So the derivative of K with respect to A. Let's go for a bonus. $60 seconds.
Would it be 1/2 E over L times A squared?
No. Let's put it in another way. You remember, for example, in calculus when you had f, I'm writing on the top right with a red pen, f, when we had f is equal to, for example, x squared times y divided by z. This was like a function of 3 variables. Then if I wanted to find the derivative of f with respect to, for example, y, then that would be exactly similar to the case that in this relation, everything is constant except y. So y only changes. So that means this relation is like constant times y. And what is that constant? That constant is x2 over z. So in this case, if I wanted to find partial f with respect to y, that's going to be simply x2 over z, because the y is only the changing variable. Now, using the same hint, you tell me what is partial k, partial a. Brooke, good job. Bonus, please email to this class. That's right, E over L. E over L. The answer is E over L. Because you is A. So the rest are like a constant coefficient. You see that? So now I want to do, for example, so the first thing I got it. Now let's go to the second one. Derivative of k with respect to E. What do I put here? A over L. A over L. Perfect. And finally, the derivative of k with respect to L. What should I put here? Derivative of k with respect to L. No. Well, let's try it one more time. Let's go back again to the calculus, but this one, calculus 1. If we had a function 1 over x, and I wanted to take the derivative of dy dx, what would I get? 1 over x. Dy over dx, if I only had y is equal to 1 over x. Here, that's highlighted. If I had y is equal to 1 over x, and I wanted to take the derivative of y with respect to x, what do I get?
Natural log?
No. That is the integral. That is the opposite to the derivative. Well, if you take an integral, then you get natural log of x. But right now we want to do derivative. So guys, you remember? Yes, Brooke, thank you so much. That's right. Let's go back to this y is 1 over x. Derivative dy over dx is -1 over x squared. Now you may ask, how come? Well, first of all, this I wish we had more time so I could teach you this calculus review or things like that. But unfortunately, really, we don't have time to go over it. But you do have time. You can, in the weekend, you can go over your calculus book and review these derivatives and everything. But you remember when we had equation in this y is equal to x to the power, for example, A, arbitrary. Then dy dx was a x2 power subtracted by 1. You remember that formula? We had this in calculus 1, basic calculus. Now here, a is -1. So if in this case, when I have, let's go to another slide. Let's go back here, one more slide. When I have y is equal to 1 over x, that means if I take this x to the top, I have y is equal to x to -1. And if I want to use that formula, if y is equal to x to a, dy dx is equal to ax a minus 1. This was the formula in the standard table of derivatives, okay? So if I want to use this formula, then I dy dx is -1, because -1 is a, times x to whatever the power is subtracted by 1. So you get -2. Now bring this to the bottom. So you get -1 staying in the top divided by x squared, right? Now go back to the example. Now my spring constant, instead of y, I just simply say k is ae over L. Okay? Now I want to do derivative of k, derivative of k when, let's write it with the only, different color, only L changes. So it's L here is like X. So what do I get? Well, I treat, this is my only variable that changes. I treat it like this X. So everything else constant. So let's group them together. This will group to a constant. Take it out of derivative. So you say dk dl is equal to, take that constant out. So you get ae, then take the derivative d dn 1 over L. You see that? And then you have ae times the derivative of 1 over L is what? -1 over L. I put them together. Delta k over k, delta k over L is going to be ae over L squared -1. That's it. So if I want to put them all together, if I want to combine all this information together, if I go back to the previous derivatives that I had here, I have already found them. So I want to just put them all to one framework. So my delta k was delta k with respect to a, delta a, plus delta k with respect to L, sorry, E, delta E, plus delta partial K, partial L, delta L, right? This was my, if I go back to the previous slide, my standard vector calculus differential relation, this relation highlighted in green, in yellow, sorry, okay? So just look at this equation. Well, sometimes you get negative multiplied by negative, positive. Sometimes you get positive multiplied by negative, you get a negative. So in the worst case scenario, my maximum, because we're talking about the maximum, delta K max, worst scenario, worst case scenario happens when you actually do absolute value of this, absolute value of delta K over A, absolute value of delta A, the magnitude, plus absolute value of delta K over E, absolute value of delta E plus absolute value. Don't forget this absolute value of delta K over L, absolute value of L. You see that? So let's substitute all this information in this relation to find delta K worst case scenario. Okay, so I'm gonna make another slide. So delta K worst case scenario is absolute value delta partial K A delta A plus partial K partial E delta E plus partial K partial L delta L with absolute value. Now let's go grab this formula and put it here. So what should I put for delta K over A? Go back and review your formula. What should I put here? Let's go substitute. What was the formula for delta K over A?
Absolute value E over L.
Exactly. Absolute value of E over, and look, because is always a positive number already, right? And modulo of elasticity also a positive number. Although I have absolute value here, but I don't simply write it to make it simpler because they are always positive, right? I don't need to worry about it. And don't forget, these are my average length, average absolute value. We already have it in the table. You see that? So we should put average here. And don't forget that we already have absolute value delta. Now let's substitute the formula for delta K over E, or partial K partial E. What was that formula? That formula was absolute value of A bar over L bar, right? And because this is already A is always positive, you see, I don't put absolute value because have you ever seen an area that is negative? The black hole. So area is always positive, length is always positive, so I don't put absolute value here. Okay? And don't forget that there is already absolute value of delta E. Now we go to the last one. What should I put here for partial K partial L? Absolute value of partial K partial L. Going back to the formulas, we just wrote it in the previous slide.
At the absolute value of the negative EK over L squared.
Yeah. So when you do that, we say absolute value of AE over L squared. Absolute value of this negative, right? And when we take an absolute value, what happens here? We get rid of that negative sign right there. So it becomes A bar, E bar, L bar squared times already absolute value delta. So that's my delta K, worst case scenario, because we put absolute values. So in the report, you see that in the table, it's talking about delta K over K theory. Okay. Now, if you put K theory, what was K theory? K was A over L in this example. And these are all averages, right? Go back to your notes. K was A bar, E bar over L bar. Right? Now put it here. What do I get? This becomes, the top is delta K, the bottom is K. So delta K was E bar, L bar, delta A absolute value, plus, excuse me, A bar, L bar, E plus bar, E bar, L bar square, delta L divided by the bottom is A bar, E bar, L bar. Now simplify that. What do we get? You see, you can expand this fraction. So this becomes, excuse me, this cancel out with this. This one goes with that. This goes with this. This goes with that. All can. And this goes with this. So your final equation becomes a beautiful, simple equation. Absolute value of delta A over A average plus absolute value of delta E over E average plus absolute value of delta L over L average. That's your delta K over K predicted in the table. Look at this equation. Isn't that gorgeous? So how do you put these numbers here? Where you go to the table, you already had delta. You just take an absolute value, put it here. You have L average, you put it here from table. Table of measurement. You have error in E, put it here. Average in E, put it here. Error in A, average in A. And then you get delta K over K. When you get delta K over K, then you come to this table and put it right here in this table, right here. So put a green value here and put a check mark. So we have already done that. We discussed that. We discussed this using two methods, either high-low, partial. Okay. Now I want to give you another example. And I want to consider this as a final figure. So this is a great bonus. If you do this right now, today in the class, then you don't need to do final exam. And only one student, the first person that can do that, takes the final exam. Okay? So here is the problem. K is equal to, hold on, let's use black. K is equal to G M1 M2 R square. Okay, then find delta K over K. The relation for delta K over K. So this spring constant is given. This relation, you don't need to drive it, this is given to you, okay? All I'm asking is to find delta K over K predicted, that means theory, that means you should do partial derivative, partial using partial derivative method. What is the delta k over k predicted using partial derivative method? Now, before we solve this, what would be, can I use high-low to find delta k over k? Yes or no?
Yes.
Yes, because it's just simple fraction, right? So what would be delta k using high-low? It's going to be k max minus k min divided by 2, okay? And what is k max? K max is g plus delta g times m1 plus delta m1 times m delta m2 divided by, that's your k max, r minus delta r square. Okay, and what is the k min? G minus delta g. Of course, these are absolute values again, but you know that most of these are already positive numbers. G minus delta g times m minus m1 minus delta m1 times delta m2 divided by r plus delta r square. And then you compute these two decimals and then you put it here. And max minus min divided by 2 gives you delta k. Okay? But in this question, I'm asking to you to find the using partial derivative and give me the formula in partial formula, a very simple, beautiful formula after simplification. So you have to find delta k divided by k average, do a simplification, and then you find the formula. Now let's assign a 10 minutes time to this. So let's wait to 3 p.m. So if you email, when you do it, I mean, you should be able to do it probably in 4 or 5 minutes. Simplify it, and then again, take a photo, email it to me. The first person that I get on my mailbox will get the final exam waiver, okay? Let me go grab some coffee, I'll be back. Okay, if you have done it, please email it to me. Do not use Canvas. So email, let me put my email in the chat room. My email, chat, hopefully, see here, chat. Email is my first name dash last name @utc.edu. Please email your PDF file or document directly to this email. I wait another 60 seconds. I know some of you have done it, but email it to them. And then I solve the problem myself. I'm still waiting on your emails. Okay. See, I got another email. All right. very, very close, but still needs a little bit touch in the last term. Delta K over R, partial K, partial R, delta R. Let's see. When you simplify, you see Brooke got very, very close, super close, but still is not. There is a small mistake somewhere in the very last term. So we're gonna have more opportunity. I mean, this is not gonna definitely be the very last. Hopefully, we're going to have at least 2. So here, I want to solve myself. I write K is equal to a function of, how many variables do I have here? 4 variables, G, M1, M2, and R. These are 4 variables involved in this problem. So if I want to find delta K, right, the differential of that K, that's going to be using the same formula that I from the vector list. You say the partial derivative of K with respect to the first variable, which is G, delta G, plus partial derivative with respect to the second variable, which is M1, delta M1, and go on, partial K M2, delta M2, partial K, partial R, delta R. So G delta G, M1 delta M1, M2 delta L2, delta M2, and R. And don't forget, because we consider worst case scenario, you should consider the absolute values of these guys, because we want to get the total sum. We don't want negative term to subtract and minimize it, reduce it, right? So all I need in order to be successfully evaluate this and simplify is to find this derivative, this derivative, this derivative, and this derivative, right? So let's do your delta K is going to be right here. What is that derivative here? That derivative is simply M1. Look at this relation on the top. I'm pointing with the red arrow to that, this relation. If you consider your variable to be only G, the rest constant, you see, this entire thing becomes a constant. So group them together, and that constant times G. Now you want to find partial G. Then simply that constant, M1 and 2 over R squared, the coefficient of G. Okay? Inside absolute value times delta G. So I got rid of the first term plus the second term, partial K, partial M1. Now you realize immediately that's going to be G M2 over R squared, because your only variable is M1, G M2 over R squared, inside absolute value delta M1. Now you go to the next one. What about partial derivative with respect to M2? Well, the rest become coefficient. So you get G M1 over R squared inside absolute value, right? Delta M2 plus finally partial K with respect to R. Now this is probably the hardest part. So how can I find partial K with respect to R? Look at this equation on the top. The only variable is R, the changing variable here. The rest become constant. So in fact, you can group them together. Say G, M1, M2 is just a constant on the top. And then you have a variable R squared in the bottom. How do you take the derivative of that with respect to R? Well, take this to the top. In fact, r squared, if you bring it to the top, you get r to negative 2. You see that? And when you take the derivative, it becomes the constant time negative 2 r to the negative 3 using the formula that I introduced. So it becomes negative 2. And what is that constant? G m1 m2 times r, and then you subtract power by 1, negative 3. That's it. And when you put it in the absolute value, you get off this negative number. So this becomes positive, right? So what I'm going to do, I'm going to put that here. I wish I had more space. Can I, let's see if I can grab this thing and just drag it to the left. Like cut and paste it to the left, because I don't have a space to put that. Well, I try. So then here, this little thing, put it like that. I'll write it down. So you have 2 times G M1 M2 R to the negative 3, which I just simply bring this negative 3 to the bottom of this, so it becomes R positive 3. So 2 G M1 M2 R to the positive 3. That is simply this derivative. Don't forget, we'll have a delta R inside absolute value from here. So this thing is just the top, delta K. And if I want to divide this guy by K, right, I need to use this K in the bottom. So let's do that. Let's put it here, G M1 M2 R squared. Now simplify. What do I get if I simplify and expand? Expand and simplify. This is going to cancel out with this. It's going to cancel out with this. Cancel out with this. So the first thing you get is delta G over G. And you know that when we say G here, we're talking about average. These are all average. You see, these are all average. So I just simply don't put average here, as you know. So you get delta G over G inside absolute value, plus, what do I get from the second one? I'll wait on your response. If you simplify, expand it, and simplify the second term, what do I get?
Is it M1 times delta M1?
The delta M1 is on the top. So you see, for the second one, this will cancel with this M2, R2 cancel with R2, G cancel with G. So what you get delta M inside value, but look, this is on the top, divided by bottom, which is M1. This is the second term. What do I get for the third term? Yes, that's right. The third term you get G cancel with G, M1 cancel with M1, R2 cancel with R2, you get delta M2 over M2. And what do I get for the last term? Now this is the interesting part. the last term, let me write it here. On the top, look at here. On the top, you have 2g m1 m2 over r cube delta r. This is the on term you have g m1 m2 over r squared. So if I simplify this fraction, what do I get? If I simplify this fraction, what do I get? Well, g obviously is going to cancel. That's right. 2 over r, the Brooke is missing something. 2 divided by r times, you see this cancel out with this. G cancel out with g, m1 goes away, m2 goes away. R3 cancel out with r2, but still you get 1 r in the bottom. And then also you get 2. So you get 2 on the top, 1 bar r in the bottom, exactly the way Brooke did. But look, don't forget about that. You have a, exactly. Thanks, Brooke. You have a delta r here. This absolute delta r. So I put here. That's it. So this colorful, beautiful, simple equation is your delta k over k predicted that you put it in a table. But look, you don't need to put this relation in table. What you do, you go to your measurement data and you grab your data and substitute here. For example, your delta G is 1.2, whatever, G is whatever. This is a number, this is a number, this is a number, this number, this is a number, this is a number. You put it there, put it in a calculator. Finally, you get a number for this guy. And then you go to this table. Let's go back to the table. And then you put it right here. Okay, now, after such a long time right now, we are halfway through this table. And what about the observations? So we have covered 50% of this table. 2 columns on the left. What about 2 columns on the right? K observed, delta K over K observed. And then we go to relative error. These are easy. Relative error, max error. They have just a formula. You use that formula to find the error. But what about these 2? Well, let's start. I mean, right now, I don't think we're going to efficiency. If I try to cover it today, it's probably not good for students because right now we're almost talking for 2 hours and 18 minutes. So let's set up another class. Let's say today, Friday. I'm going to set up another class Friday, 1 p.m. Friday. Okay. And I am going to cover this K observed and delta K over K observed. I'm going to cover these 2 topics there. And because you need to have a fresh memory. I mean, you need to, right now, it's not going to be beneficial to you. It's going to be confusing. You need to take rest, practice, and then we're going to cover these 2. But I'm going to be an assignment by Friday. Please start. So let's make another slide. Assignment. So this is what you do by Friday, 1 p.m. Step 1, read through the helical spring lab. Step one, just read the theory, get the spring constant formula, and see what are the parameters involved in the spring constant, and two, find delta K over K using both for this spring, helical spring, for this particular equation report. Find delta K over K using both high-low method and partial derivative. Do both of them. Okay? Do both of them. Because and if you do either one of them, it's just fine. But for this, do both of them. 3, send me, when I say send, I mean scan and send. Scan your derivation, scan, and send me your derivation. So this is, let's call it assignment 1. Assignment 1 preparation. So I'm going to post this assignment and I'm going to assign it a grade that you go through these 3 steps. For example, this delta K over K, there is a equation in your manual. Equation already in the manual. Now look, that equation may or may not be correct. You have to derive it yourself from scratch, from basic vector calculus. The basic vector calculus is delta K, partial K with respect to var1, delta var1, plus partial K, partial var2, variable 2, delta variable 2, and so on, right? You have to start from here, calculus 2, and end up with the formula to validate either the formula in the lab manual is correct or not, or is not correct. Okay? And then you send me this thing by uploading on Canvas. Send the scan, upload on Canvas. The deadline is going also to be Friday. Friday on. I want us to do it just before the class, so when we start talking about the next topic, which is observation, I want you to completely understand all this thing in the theory world, in the world of theoretical delta K over K, okay? So let's wrap it up today. So what we discussed was everything except these 2 columns that are with yellow. And these 2 last columns are not really hard. They have a formula. You don't need to understand it. But these 2 columns in yellow that are painted, they need some understanding, right? So we are going to cover it Friday 1 p.m. Highlighted Friday 1 p.m. Don't forget that. And then also don't forget, you need to do this assignment. You may screenshot of this because we may lose it. So you need to do this assignment. I put a link to it online and upload your assignment so I can grade it, okay? Any question? Any question? Okay, if you and then let's go back to your stop share and the video, the class video. Let's see who is in the class. Okay, we only have 3 participants. Okay. Well, I want to this class today right now, and I'll see you guys tomorrow. Okay. Bye.